Okay, so we're a few minutes past, so I will go ahead and start. Welcome to the device tree and secure firmware dynamic configuration session. So this is not my session, this is really Dan's session, but this also is a chance for me to stand up for just a couple of minutes and talk about what's going on in the device tree world. So I don't have any slides, I don't really have a whole lot of content here, but I wanted to give an update on where things are at. About a year and a half ago, we kicked off devicetree.org, which was to take all the best practices, all the things that we're doing with device tree, take ePapper and start forming it into, or to update the formal documents so that we've got something, a working set that's going to, a working specification that's usable by more than just Linux and more than just you. That stalled over a year and a half, in part because I ran away and worked for another company for a bit and wasn't doing any DT work. There's been a little bit of activity, but things are kicking off again, and I'm back. Part of my job is working on device tree. I'm responsible for the specification. We've got a number of interesting topics that have come up just in recent months. And there is going to be, the first major event is going to be next month in conjunction with Kernel Summit in Prague, where there's going to be a half-day device tree workshop on the Thursday of ELCE and Kernel Summit. So anyone who's interested in that, who has technical topics, should go, if you go to, it was posted on the device tree mailing list, the details. You can come talk to me about the details. Linux Foundation website about Kernel Summit is there as well. And then there's a wiki page on the Linux, believe it or not, the Linux Plumbers wiki page has the details about the workshop at Kernel Summit. So go and take a look at that if there's any topics that you want to talk about. The thing to do is to propose it on the wiki page or to email the mailing list. In terms of technical topics of what is on the radar and what are the things that need to be solved in short order, there are currently two competing solutions that are being discussed for dealing with both schema validation of device tree data and also how to produce documentation from the schema files. There's Pantelis, I can never pronounce his last name. So anyway, Pantelis has a solution that he's using. He's got a JSON encoding for device tree, and then he's using Berkeley Packet Filter, eBPF, for doing schema validation. And I've been working with something similar for the encoding in YAML, but instead of using eBPF, I've been looking at JSON schema as the engine. So that's one of the topics. I think we're going to talk about, there's improved tooling for how to make use of device tree, overlays and how to actually have an overlay manager and a connector specification in there is one of the technical topics. And after Nicholas's presentation on Monday, where he showed just how bad DT is on memory usage on very small systems, that probably will be a topic as well. So,
oh, I missed that.
Yes, it was all kinds of fun. I had to hang my head. So that's what's going on in the device tree world. I'm going to pause very briefly for questions, and then I'm going to turn it over to Dan. So any questions on device tree core work? Stuart.
So what's the state of the spec? Like, what's the state of the spec? There was a draft of that a year and a half ago or so that we kind of put together, and I guess so that's out there now. You can, or is it kind of quote officially published?
It's not. It's not officially published in terms of it's not a 1.0. There's a 0.1 version of the spec, which is at about the same level as ePapper, but with a number of things cleaned up. That needs some work. Part of what has stalled the spec is wanting to transition towards having having the bindings described in YAML or something that can actually be used for the schema validation as well. And so every time I went to work on the spec, I got distracted with, I don't want to write just text for describing this. If we're going to have a spec, then we should have it should be designed in a way that can be used with the tooling.
But there are patches happening or welcome.
Yeah.
So there are various fixes going in, and there's some additions pending for GPIO maps, which is one of the, well, it's actually more general maps, so generalizing the IRQ map, and that's needed for connector binding. So that's pending. Any reviews would be welcome. And it builds in Travis CI now too.
Any other questions? Okay, great. Well, I can turn over to Dan then.
Thanks, Glenn. Just put my machine in.
Sorry about this, folks. So that's the problem with the cable, I think. Maybe I'll summarise what we're trying to talk about here at least before we maybe a slide for that. So this is there was a session of the same title at Budapest, and basically that was quite a short session, only 25 minutes, and it kind of got compressed, and there was a lot of discussion happening, so but not a lot of conclusion. So I kind of wanted to pick this up, especially as this was probably going to affect my area. There's just a firmware or other secure firmware quite greatly. So I'm not. This session isn't. You don't need to understand what happened in that session. I was going to go from scratch, but I really could do with these slides to demonstrate what I'm talking about.
Let me see if I can get them up on my laptop.
All right. Yeah.
You emailed them, right?
Yeah. So a different connector for amenities flow forwards.
Anybody have a USB-C? HDMI?
I do.
I can borrow it.
I think I do.
seems to be an issue with the connector, but maybe we'll have better luck. There we go. Oh, well done. Good stuff.
You really don't need to see my. Oh, and I've lost it. There it is. Okay.
Okay, that should work. Thanks.
Well, it's going to require small, so I'll just sit here.
Okay, yeah, so, well, the first slide is pretty much what I just said, is that we're trying to read just to say this is a recap of what happened in Budapest. So the kind of pithy summary from that, which I'll go into more detail later, is that, you know, doing some kind of device tree manipulation use of in secure firmware can be a good thing for some platforms and use cases, but it's not going to satisfy everybody's needs, so we need some flexibility here. There's especially concerns around RAM footprint and complexity and performance costs, which apparently that's been justified in some cases, as Grant said in an earlier session this week, which I missed unfortunately. But we still need some firmware configurability even on those platforms. So yeah, I'll now rewind to the actual use cases we're trying to solve here for people who are completely new to this. So, firstly, some partners just want to be able to do some configuration of secure firmware features, basically switch things on and off, or maybe choose which exception level to start the normal world in, that kind of thing. Fairly simple stuff. Eventually, there might be something more sophisticated, like actually choosing how the images are laid out in memory, and just moving them around and fitting them well without having to rebuild the firmware. See, that requires other changes, at least in just firmware to support positioning and executable support. But that's kind of where we'd like to get to.
That's not like device tree related, is it? This first use case. That first use case is more. Isn't this first use case more related to have to have stuff earlier on in the process to figure out where to put these different images, BL2 and BL3, or is that what you're talking about here? That early stuff.
So when I'm talking about dynamic configuration, I basically mean doing stuff as the software is executed rather than build time. That's all we're talking about. Dynamic. So I'm trying to use the term dynamic configuration to be more general than just what device tree solves. Okay. And that's kind of the conclusion I'll come to on my next slide, is what you just said. So the second use case is more traditional kernel device tree use case, which is configuring the firmware using some description of the hardware. So, what kind of the nodes, what CPU nodes and cluster nodes to represent the PSCI topology, maybe what debug console you're using, any other devices used by the secure world. Number 3 is kind of a subtle variation on that, is where you may be doing some configuration of some secure hardware, but it's kind of very specific to a particular component, so it's not really going to be useful outside, certainly not useful in the normal world, and it's probably only useful to a very specific component, so maybe configuration of the DDR training parameters or some security policy information of what bus masters can see what kind of memory. And then number 4 is kind of the same thing, but done, using the same configuration, a centralized configuration, but doing some processing as a pre-build step to end up with still a static firmware at the end of it. So you've still got the kind of benefits of a tight final binary executing fast, but you've got some kind of centralized configuration mechanism rather than kind of a static build flags scattered throughout, the build system and the code. And then finally, there's actually not just using hardware configuration, but modifying that as seen by other software. So maybe say the kernel device tree might have it will show the full memory that's available in the platform, and then the secure firmware might reserve some of that and pass that on down the line. And similarly, the UEFI might choose the kernel boot arguments or whatever other normal world firmware. So we're trying to solve all of those. So some observations from that. So some of the configuration can be shared by various components, especially all the hardware device information. This is where DT is certainly a good fit and has been used widely. But some of the other configuration are either maybe used by a single component, or it may be secret information. Maybe you don't really want to represent that to other components, or it may only may not really relate to hardware at all. So you could use device tree for this, but it doesn't have to be device tree. It could be something else, and it doesn't necessarily need to be in the kernel device tree, even if you use the device tree format. Another important consideration is the when you've got secure boot enabled, or trusted board boot is the ARM term. So there's an ARM specification for trusted board boot requirements. Any dynamic configuration you have also has to be authenticated along with the firmware itself. Not only does it have to be authenticated, it has to be authenticated using the appropriate certificate for that firmware. And I'll come on to that a little bit later on the impact on the chain of trust. And finally, what I'm hearing is a lot of platforms need a lot of flexibility here. So although device tree, just doing everything in the kernel device tree might work on a fully vertically integrated platform, it's not going to work for everyone. So some partners only want dynamic configuration in some of the firmware, not all of it, or maybe on a per image basis. And then even if dynamic configuration is enabled, they still want the option to fall back to a static configuration if they want to in, say, the final production image. And the file format to use as well, you need some flexibility there. So in case they want some kind of really tight, memory representation instead of something more broadly applicable like device tree. So this all leads me to think that we need a single hardware configuration, which might be device tree, or plus a firmware configuration per component. Now you don't have to have all this, but that's in the worst case scenario, that's what you would have. So I've got a diagram on the next slide which kind of shows you this worst case scenario. But I don't expect this to be the case in initial platforms at least. So this sorry, I'm clicking on front. So this is a diagram I've modified from an ARM trusted firmware previous presentation. So I'm going to use kind of partly ARM trusted firmware terminology and partly trusted board boot requirements terminology. So the typical boot flow in an ARM trusted firmware based boot flow is you have a BL1 with some ROM code which loads BL2, which loads some third level images which include the runtime firmware, the main part of ARM trusted firmware, BL3.1, trusted operating system, BL3.2, and the normal world firmware, BL3.3, which then loads the kernel. So the modification here is the ROM code may want to load, well, it would first load this, what I'm calling the trusted boot firmware config, because this is TBR language. The trusted boot firmware is BL2 in more general terms. And so it'd load this, the ROM would load this configuration and it would get some information out of it. One of the pieces of information would be the address where this hardware configuration lives. And so then it would load the hardware configuration once it knows that, and then may use some information there before handing off control to BL2. BL2 can use the same hardware configuration, but it will reload the trusted boot firmware configuration itself. So the configuration is shared between BL1 and BL2 in this case. But then for the other third level images, they all have their own firmware configuration that goes along with the image that is loaded. There's some complications around security. If your secure firmware is in on-chip memory, then it might not be considered secure to load this hardware configuration into DRAM, because that could be subject to probe attacks. So that's why I initially loaded it into on-chip memory, and then maybe it has some later step that would copy that into normal world memory, DRAM. Yeah, so that's kind of the most complex use case I see. But the rest of the slides sort of build on this, so hopefully that's reasonably clear. If there's any questions on that, now's probably a good time to ask.
Question, why do you need the hardware config? Why do you need the hardware config in that early stage? Just because you're only using it way later down.
Yes, you would only do that if say the ROM code itself needed that hardware configuration. If say the first thing to use it was BL2, then BL2 could be the one that loads that instead.
But why even him loading it when? Because all the other guys have their own configs until the hardware.
Yeah, but they're all sharing this hardware configuration. So this is say this contains some information about where a device is. Assuming so here we're assuming some of this early firmware is wanting some information out of, say, the kernel device tree, where a particular device is. It's the same kernel device.
But you also have the TV firmware config and SOC firmware config.
Yeah.
They're not overlapping the functionality of the HW config.
I'll come on to what's in this information, what's in these configurations in a minute. But there could be overlap potentially, you're right.
So today, everything's hard-coded in those other stages? So is the hardware config is hard-coded today, and what we're proposing is that that the firmware would not have hard-coded assumptions about?
Yeah, currently untrusted firmware doesn't use device tree at all. So everything's static, yeah, all the device information. So that's one of the use cases, is just simply use the kernel device tree basically and secure firmware to get device information. Okay, move on. So the file format. So I slightly rejigged this on my slides, but yeah, basically I'm proposing the device tree is the default format for these config files, but it doesn't have to be that. And the idea is to add support in the generic make files for building the device trees from source and adding them to what we call firmware image package in trusted firmware terminology. So the firmware image package is the thing that contains all the RAM loaded firmware plus the certificates. So it's kind of like a mini file system. And so you could add these configs to that as well. So we need some library functions to be used at runtime to parse the device tree and populate any kind of global data used by the firmware for those features. And maybe later we could also consider some additional tools to convert the device tree into code and then produce a centralized static configuration. I know for example, the Zephyr project has this kind of functionality, so we're looking to maybe leveraging some of the stuff there. But an important consideration here, the BL2 code, the thing that loads the third level image, is kind of agnostic to the format. The config is just another bit of binary for it to authenticate. That's assuming that the file formats themselves are kind of self-discoverable. The code that needs to use the config can just say, look at a magic number at the start of the file to find out what the format is. But the stuff that does all the loading and authentication doesn't need to care about that. But to solve the problem of some platforms not wanting to process the device tree format, there are various options for how you deal with that. You can deal with that at runtime by, say, after each image is loaded, converting the device tree into some other lighter weight format that target image can process, which would be less onerous on that particular image. Although that's more work at runtime, obviously. Another option could be just compile it into the required format in the make file and add that format instead to the bit. Or you could just add the blob directly, so the secure firmware tools don't even understand what the format is. And if we see the kind of other formats that become useful, maybe the starting platform code, but we could kind of migrate that into more generic code if that proves to be useful later. Okay, just a few comments on the there's a kind of conventional handoff interface for the on entry to the main ARM trusted firmware. We use this the X0 and X1 for specific reasons. The X0 we use this has this BL params structure, which is an ARM trusted firmware structure, which just describes the images that need the image execution order. So it contains information about the secure OS and the normal world entry point that you can pass through the chain. And X1 is for any other platform specific information. So I'm proposing to sort of rejig this round. Actually, my latest version, I kind of switched X1 and X2 here, so but it doesn't really make a huge difference. I'll on the when we upload the slides, I'll upload the latest version, which shows my proposal, which is actually X1 would be the hardware config and X2 would be the soft firmware config. And then for the entry into the other images, we again use the one for the hardware config and one for the particular target BL's config. And the idea is then we could then pass this information into these platform setup functions in the firmware. There's a few kind of compatibility concerns there about passing new information, new arguments, but I'm sure we can resolve those. But this is all still under the control of the platform, and it's just a convention at least to start with. But if we get to a stage where this is used very, everywhere and very widely, we can start to move this from the completely platform choice into what we call the plat common code. So plat common is code in ARM trusted firmware is used for things we expect most platforms to use unless they have a good reason not to. So they can still override it, but it would be this is the default choice. So what's in this configuration context, to come to your earlier question? So as I say, the hardware config I see as a one-to-one mapping with a device tree, kernel device tree. Maybe you could add some additional nodes in there if there's any stuff that new use cases we see that the secure firmware needs to see. The trusted boot firmware config used by BL1 and BL2, that's probably going to be the most complex one, at least in the short term, because that contains where to load the hardware config, and eventually any address and size information for all the other images, where to load them, and for the certificates and configurations, and which ones overlay which other ones, and stuff like that. And then again, this information generates BL param structure as well. Beyond that, you could even look at actually representing the chain of trust, so what the certificates look like, and how you authenticate them, whether you use hashes or what algorithms, and whether you use non-volatile counters for rollback and things like that. And then basically all the other sort of on-off features as well, whether you switch secure views on or any other features in the firmware. And then the other firmware configs can basically, they can add what they want, and I'll speculate a little while in what that could be in my proposed development plan here.
So right now for your chain of trust, you have that array of, I can't remember what it's called. There's that array of image descriptors that describe all the certificates and also what things. So you're saying that image descriptor array you would want to move to the firmware config.
Precisely, yeah, that.
Would it basically be the same structure?
The same information, yeah.
Same structure and everything, just dropped as a sub field of the record?
So yeah, in the code now, as you say, there's a static file which can describe your particular image descriptors, and then we provide some utility functions to convert that into the runtime structures needed by the code. We just, you put the same information in the device tree, and provide some alternative utility code to generate exactly the same information.
But it would just be in a device tree source format, and then compile it into it.
Yeah.
So have you looked into U-boot, because this is what is used there already? So there's some place for SPL, smaller parts, which take device tree, convert this into something which will be compiled in. So there's some nice abstraction from a device driver level. You don't need to care whether it's actual device tree or something that has been transformed.
Yeah, we've looked a little bit at UBoots, and that's the similar concept. As I said there, we could see for some platforms where they just want some very specific configuration information, they could stick there. But like I say, I want to concentrate on the broadest appeal to start with, even if that's not the most efficient format, and let platforms innovate as they need to do, and then we can borrow from other projects as well. Just a bit more of a note on the chain of trust. So this is a kind of subset of the certificate structure from the Trust Support Boot Requirements document. So in this you have kind of root and trust key in one-time programmable memory, which is used to verify. It's got a trusted boot firmware certificate. Basically, that contains an extension which is a hash of the BL2 image, and so you can use that to authenticate BL2. And then there's a trusted key certificate, so it kind of devolves ownership of the keys to other entities effectively by using this additional keys, trusted world public key and a normal world public key. And the trusted world public key then is used in two other certificates, one for the SOC firmware, otherwise known as BL3.1, and then the trusted OS firmware, i.e. the trusted OS. And then similarly on the normal world side. So actually the only way this would change, I expect, is you just add some additional stuff into the existing certificates. So the hardware config and the trusted boot firmware config would go into this certificate, and then the individual firmware configs would go into the appropriate certificate. So not a massive change on the actual chain of trust, which is good. I don't really want to mess around with that too much. And we already have precedent in just a firmware for adding additional hashes into certificates, so that shouldn't be a great deal of work. Okay, it's not going to be easy to do all of this. So we know that just a firmware build system's already kind of struggling to cope with all the stuff we're putting in there, all the different configurations. And this implies lots more targets and defines, and we could just get out of control quite easily. So it might be the right time to consider an overhaul. I mean, this is an old version of the slides. I said kconfig style system, and maybe I don't mean that. Maybe I mean something like what Zephyr uses for generating static configuration from a device tree format. But there could be other solutions. I haven't thought too deeply into that, but it is a concern. Some partners have a concern about the configuration may be required before the MMU is enabled, and so that's got specific concerns around performance if you're trying to do some parsing before the MMU is enabled. So for example, trying to get some console information when you're trying to do the MMU debug, get some debug information of the actual MMU setup itself. That console information might be something is stored in a config. Or, for example, there may be some firmware that needs to be loaded before you've actually done the platform setup where the MMU is set up. So, the example here is the power control firmware, which might set up DDR. You can't really do your platform setup until DDR is available. You can't load anything into DDR. So, we're basically assuming for now either this information is static if needed, or we can do the parsing later after the MMU is enabled, so in the platform setup instead, or platforms can choose their own config format in this case, and that's more time. But that's not a problem I'm trying to solve immediately. One other implication of this is that if we start actually compiling the device tree source files and loading them into the FIP and doing it at runtime, that implies that platforms that use trusted firmware BL1 and 2 will start submitting their kernel device trees when they upstream their ports into firmware. So it could end up being the kind of de facto upstream for kernel device trees, which might be an unintended consequence. I don't know if anyone's got any comments on that. I mean, I think ideally we'd still want device trees to live in somewhere else.
So on the topic of where device trees are actually maintained, it's been controversial. Like there's been a lot of pressure to keep device trees in the kernel, particularly because that's been the process. You build your kernel, you build your device tree, and now it gets put onto the board, and that's very much the embedded use case. As it makes sense to have kind of that platform split. And on platforms that are using ARM trusted firmware and have a kind of a solid build that goes with that, there's less pressure then on having the DT maintained in the kernel. So I'm not too worried about that, and it certainly makes sense from the model perspective of keeping DT platform information with the platform firmware, because that split between platform side of things and operating system side.
But it would mean that for stuff like DDR parameters that maybe live in the ARM firmware which have no bindings in the kernel. As far as I know, this has been never found to have bindings in the kernel which are not used by the kernel, right? So that would mean that once you have at least a single piece of one node which is not handled by the kernel, that basically cannot live.
You think that's a specific example of the? Sorry.
Totally fine.
There's Molly bindings. There's Molly bindings.
Okay. Yeah.
I expected that specific example of DDR config, which, as you say, the kernel doesn't care about. That wouldn't be in the kernel device tree. That would be in the TVB firmware config.
There could be one magic super DT, which contains all the stuff. So it contains the kernel nodes, it contains the nodes that only the firmware cares about, and then firmware could decide to either remove them or just leave them alone. That would avoid having different parts of the DT.
You could do it, or you could just put it in two different places, and then you don't need to do any processing at runtime. Yeah, so it could work the way you say that. One of the points here is that this is very flexible, and platforms can choose to do it how they want. Okay, this is my last slide, I think. Just a kind of rough implementation plan. You know, don't hold us to this. We haven't really planned this out yet. But the idea would be that in the first phase would be trying to just get all the infrastructure in place for doing this. So adding support to build the device tree and kind of pipe clean the process with using a minimal configuration file, which maybe this TVB firmware config would just contain simply the hardware config's base address, where to load it, and then you pipe clean the whole process with that. And then updating the reference platforms to load these things and use them in the reference platform releases. And then once that's represented, then it kind of unlocks other platforms to do the same thing. And then with phase 2, we could then hopefully kind of parallelize the activity then to add other configuration and information into the other images. So adding other stuff into the TV firmware config, like switching secure boot on and off, or the SOC firmware config. We know there's a lot of work going on at the moment to enable a new reliability, accessibility, serviceability framework on trusted firmware, and part of that is about setting up these secure partitions. Those secure partitions have a configuration associated with them, and that's information that could be represented in this SOC firmware config. And similarly, for the normal world config, you could have some stuff specifically there around the secure memory that's reserved, or that could actually be processed within the kernel device tree. Maybe EDK2 has other requirements. Opti as well could use this. We've just done quite a bit of work actually to enable the Opti header parsing in both the secure untrusted firmware and on the Opti side to allow things like the paging use case, where you load an unpaged part of Opti into one part of memory and a paged part into another part of memory. But that header information potentially could also migrate into this format as well. Or I don't want that to be the reason for it to use it, because it would involve a reasonable amount of work to achieve exactly the same thing. But I'm sure there are use cases to go along with that. And then, yeah, we're certainly getting feedback that other config formats might be useful. So could enable that. And then finally, I think we can be confident that this would be working okay if and when we've enabled position independent executable support in the firmware to allow this arbitrary moving around of images and everything just works okay. And then obviously, yeah, the new build system would be a major impact. So it's probably something to start investigation sooner rather than later, but I don't think actually landing it would be until later on. So that's me done here. I don't know if anyone's got any further comments or questions. Where's the other mic?
So first part is so you're planning in the first part to basically make the config files an additional image description. So you know how you have those image descriptions for images and inserts and stuff. You just have a fourth case, which is a config file, I assume, right?
You could do that. I mean, but as I say, I was hoping to just use the device tree rather than adding new stuff into the image descriptors. Any new stuff would be in the device tree.
Oh, okay. So the only thing I'm a little worried about here, or concerned, is I want to maybe make an image that applies to a family of SOCs that we're building. But the family of SOCs, we want to basically make it so that, for example, when you ship an SOC, we might disable crypto because of export regulations. So I need to modify the device tree to say, no, that device isn't here anymore. Mm-hmm. So the device tree is not known until maybe like runtime, until it actually checks to see, oh, geez, you know, did that key was disabling the crypto because of export? But because I don't want to actually have to have separate images for export and non-export. And similar, there's probably a handful of other cases, how many cores we have. We might want to have the same code, but with different cores enabled. So have you thought about how to make these config files effectively have some sort of if tests or runtime or something? I don't know.
I'm not quite sure I fully understand. I mean, these things can be easily editable without rebuilding the firmware, but then they are going to be. You can just recompile just that config file, and then at runtime, load those into the fit, and at runtime that will be part of the authenticated information. So if
right.
you didn't intend that to be,
but what I want is I want the config to be not static. It depends on some hardware tests at runtime. In other words, I want to have.
Oh, I see.
See, the device tree, I don't want the device tree to be static. I want the device tree to tell Linux whether or not there's the crypto stuff, but I put it in the device tree, but then I remove it because I noticed that the fuse says, oh no, this chip is restricted for export.
So the way that this will be implemented, libFTT is already part of the firmware package, and libFTT has the ability to live rebuild the device tree. So if there's things that you need to modify, and if there's nodes that you want to drop out, it's possible to, in your firmware, to do those tests, to identify the nodes that you want to redact, and I mean, remove them, do a rebuild of tell the library to compact the device tree, and that gets rid of all the old references, and then you have a pristine copy. Normally what we do is we just add a property that says disabled. But if you want to redact, the code supports it.
But I just want to make sure we have the dynamic capability.
Yes, libFTT definitely has that. libFTT.
and that library is already incorporated into the code base.
Yep.
Sorry, yeah. Either way.
What is the relationship between this one and the device tree overlay? Device tree overlay, that's right now Google has that triple to require that vendor-specific device tree part and then the SOC-specific part. Where do they play around with this plan?
I'm sure I'm qualified to answer that. I don't see it's quite the same thing. That's still all hardware description.
You're right.
My knowledge might be a bit out of date. What's the status of overlay? Has any work been done on overlay support for libFTT?
Yes, sir.
Is there? Okay.
There are boot uses.
So I think you could do that as well.
So in that case, if you wanted to apply an overlay like that boot time before you got it into before you moved into the next stage of firmware, you could do apply the overlay.
Yeah.
So this could rebuild or compress the tree. In fact, that's not even necessary. You call the function to apply the overlay, and then you have a device tree that can be passed on. So if you wanted to have several blobs within your firmware that you choose how to assemble before it's passed on, all the code you need to support that should be there.
Yeah, I mean, in this item I only showed just loading the firmware and maybe copying it, but it could be modified at any stage along the way.
Put in implementation detail.
Sorry, behind you, Graham, there's a...
I'm not that familiar with ACPI yet, but how does like this boot flow here work with an ACPI-based system? I mean, is ATF compatible with ACPI, and how would that fit into that flow?
It's currently agnostic to ACPI. That's all handled in the normal world firmware. If there is some information where you could...
Well, essentially the hardware config is what's in ACPI tables, right?
Yeah, so you could use this to, you know, if it was just a blob of information in normal to load it to normal world memory, then you could leverage that. But certainly the trusted firmware wouldn't care about what that is or what that structure is. I don't imagine.
But I guess unless you probably couldn't read it if it was a different format WAV.
So there wouldn't be a generic way of just translating device tree into ACPI, like just to take the whole thing over. That wouldn't be something supported. But a lot of the sorts of things that you'd want to do here, such as enumerating memory ranges, any of the data that shows up in the ACPI tables, everything except the DSDT. The DSDT is special, but for all of the just data tables, writing some code that translates from DT data into ACPI tables is easy. Anything that needs to manipulate the ACPI tree, the DSDT, you'd have to have a static DSDT that's AML, that as it runs in the context of the operating system, it would have to query data that's in tables or query what hardware is out there to decide how to actually instantiate that stuff. And that's just the way that ACPI works. It is possible to live runtime patch the DSDT blob, but it's really messy and nasty. And AML is executable, so it can actually figure itself out.
Any other questions? Right, that was it for me. I don't know if there's any other device tree topics anyone wants to bring up. No, I think we're good. Thank you, everyone.